Time itself might be on the verge of breaking its own rules. What if every moment we experience, every cause and effect, suddenly reversed or tangled out of order? This is not science fiction. It is a startling scientific possibility called chronological inversion. We are going to explore what happens when time collapses, from the quantum realm to the edges of black holes. By the end, you will see reality itself in a completely new way. We will uncover why the flow of time might be an illusion and what it means if the past and future begin to collide. What does it truly mean for something to be inevitable? Chronological inversion is not about building a machine to visit the past. It is the terrifying possibility that the timeline itself could snap. Imagine the very fabric of cause and effect fraying, where events do not just move backwards, but occur in a jumbled, non-sequential mess. This is a fundamental breakdown in the structure of reality, not a journey within it. The concept emerges from the deepest puzzles in theoretical physics, from the inevitable rise of entropy to the bizarre rules that govern the quantum world and the extreme warping of space near a black hole. Think of it like a river suddenly reversing its flow, or a film reel where the scenes are spliced together in a random order. The hero dies at the beginning, the couple meets for the first time at their divorce, and the seed grows from a towering tree. If such an inversion were possible, it would force us to question everything we believe about order, consequence, and the very nature of existence. Our entire understanding of the universe is built on a foundation of time moving in one direction. What happens if that foundation crumbles beneath our feet? This intellectual curiosity about time stretches back thousands of years. Ancient Greek thinkers like Plato and Aristotle wrestled with the concept, viewing time as a measurement of change rather than a tangible thing itself. But the true revolution in our understanding arrived in the early 20th century with a single, brilliant mind, Albert Einstein. His theory of relativity shattered the classical Newtonian idea of a universal clock ticking the same for everyone, everywhere. Einstein revealed that time is relative, a fluid dimension interwoven with the three dimensions of space into a single fabric called space-time. This fabric is not rigid. It bends and warps under the influence of gravity and motion. A clock on a fast-moving spaceship ticks slower than one on Earth. A clock near a massive object like a planet also runs slower relative to one in empty space. This was not just theory, it has been experimentally verified. Suddenly, time was not a constant river flowing at one speed for all, but a personal experience dependent on your own state of motion and your place in the gravitational field. This profound discovery opened a Pandora's box of possibilities, suggesting that under extreme conditions, the very flow of time could be stretched, twisted, or even potentially looped. Then came quantum mechanics, which introduced a whole new layer of strangeness. In the quantum realm, particles do not follow strict, deterministic paths. They exist in a haze of probability, and their behavior can seem to defy our everyday logic about before and after. The orderly sequence of cause and effect, so solid in our macroscopic world, becomes fuzzy and uncertain at this tiny scale. These two monumental pillars of modern physics, relativity and quantum mechanics, did not provide final answers. Instead, they gave us the mathematical and conceptual tools to finally ask the right, terrifying questions. They showed us that our classical, comfortable understanding of a one-way timeline is profoundly incomplete, setting the stage for the radical idea that time itself might not be as stable as we believe. This irreversible increase in entropy is what gives time its arrow. It is the reason we remember the past but not the future, why a shattered glass does not spontaneously reassemble itself, and why we feel time moving inexorably forward. The entire universe is on a one-way trip from a state of low entropy, like the highly ordered conditions of the Big Bang, toward a state of maximum disorder, an eventual heat death where energy is evenly spread and nothing new can happen. But this law is a statistical one, not an absolute decree. It is far more likely for a system to become more disordered than to become more ordered, which is why we never see those scattered pieces of glass leap back onto the table. The question then becomes, what if the unlikely becomes possible? What if, under conditions we do not yet fully understand, entropy could not just increase but decrease? This is the terrifying heart of chronological inversion. If entropy were to reverse its course on a universal scale, the arrow of time would not just point backwards, it would shatter. Cause and effect would unravel. You would see smoke coalesce into a log, flames cool into unburnt wood, and a forest grow backwards from ashes. The very memories in your mind would begin to rewrite themselves. Unbirthdays would precede birthdays, and the universe would rush headlong not towards its end, but towards its beginning. Some theories in quantum mechanics already hint at particles behaving in ways that seem to briefly defy this thermodynamic order. And in the unimaginable gravitational whirlpool of a black hole, where space-time is twisted into a knot, our familiar laws of physics break down entirely. It is in these extreme environments that entropy might not just decrease, but become completely chaotic and unpredictable, flickering between order and disorder with no discernible direction. This bridges a profound gap between cold, hard physics and deep philosophical wonder. The order we see in the universe, from the formation of galaxies to the beating of our own hearts, might not be a fundamental property of reality, but merely a temporary and statistically likely state in a much grander and potentially more chaotic cosmic scheme. But the quantum realm operates by a completely different set of rules, one that seems to mock our everyday experience of cause and effect. Here, at the smallest scales of existence, the very idea of a stable, linear timeline begins to dissolve into a haze of probabilities. Particles are not simply in one place at one time. They can exist in a state of superposition, meaning they are in multiple places or states all at once, until the moment they are observed. It is as if a single actor is playing every role in a play simultaneously, only choosing a specific character when the audience looks directly at the stage. This bizarre behavior is not a quirk, it is a fundamental property of the quantum world. Even more strange is the phenomenon of quantum entanglement, where two particles become linked across vast distances. Change the state of one, and its partner instantaneously changes in response, seeming to communicate faster than the speed of light. This connection appears to defy the very notion of temporal sequence, making the ideas of before and after seem almost irrelevant. These principles forced physicists to ask a profound question. If time is not a fundamental feature of the universe at this basic level, then where does our experience of its flow come from? Some interpretations, like the Wheeler-DeWitt equation, suggest that time itself might be an emergent property. It is not a primary dimension written into the fabric of the cosmos, but rather a large-scale illusion that arises from the complex quantum interactions of countless particles. It is like the wave on the ocean. The wave is not a fundamental thing, it is a pattern that emerges from the movement of countless water molecules. In this view, time is the wave, and the quantum interactions are the water. This perspective opens a door to a truly unsettling possibility: temporal instability. If time is not a fixed backdrop but an emergent phenomenon, then it could, under the right conditions, falter. In extreme quantum environments, particularly those involving the hunt for a theory of quantum gravity, the fluctuations could be so violent that they cause brief episodes of chronological chaos. For a fleeting instant, the sequence of events could stutter, invert, or even form a closed loop where cause and effect chase their own tails. This is not about traveling in time. It is about the framework for time itself momentarily glitching, like a corrupted digital file where the data packets arrive in the wrong order. The universe's most basic operating system might have a bug, one that could, under immense pressure, rewrite the script of reality itself. This warping of space-time is not a gentle curve. It is a radical distortion of reality itself. A black hole represents the most extreme example of this, a place where the fabric of space-time is not just bent but torn. Its gravitational pull is so unimaginably strong that not even light can escape its grasp, and as you approach this point of no return, something truly bizarre happens to time. Due to the intense gravity, time begins to slow down relative to an outside observer, a phenomenon known as time dilation. For someone falling into a black hole, their clock would appear from a safe distance to tick slower and slower until it finally seems to stop completely at the event horizon. But what happens beyond that horizon, at the very center, the singularity? This is where our known laws of physics cease to function. The equations of general relativity suggest that here, the warping of space-time becomes infinite. In such a state, the very concepts of before and after may lose all meaning. The orderly progression of time could potentially crumble, leading to a state of pure chronological chaos where cause and effect are no longer connected. This is not just a slowing down, it is a complete breakdown. Some solutions to Einstein's equations even allow for hypothetical paths called closed time-like curves. These are not time machines you can build, but rather potential loops or wrinkles in the fabric of spacetime itself. If they exist, an object following such a curve would eventually return to its own past, creating a loop where the effect could precede the cause. Imagine throwing a ball and watching it fly through the air, only to see it curve around and fly back into your hand from behind you before you ever threw it. This is the kind of paradoxical inversion that gravity, in its most extreme forms, could theoretically force upon the universe. It offers a tangible, though terrifying, mechanism for how the cosmic architecture could twist time into a knot from which there is no logical escape. These cosmic monsters serve as natural laboratories for the most extreme physics imaginable. At the event horizon, the point of no return, the universe presents us with one of its greatest illusions. To an outside observer, time for an object falling into the black hole appears to slow down, stretching seconds into eons until it seems to freeze completely, forever suspended at the edge. Yet, from the perspective of the object itself, its fall continues unabated. This stark paradox reveals how gravity does not just bend time, it can tear our shared experience of it into two irreconcilable realities. But the true strangeness begins once you cross that threshold. Inside the black hole, our familiar rules break down completely. General relativity suggests that within this dark heart, the roles of time and space do not just bend, they fundamentally swap. What we experience as time becomes more like a direction in space, a path you are forced to travel along, much like you are forced downward by gravity here on Earth. And what we know as space becomes a one-way street leading only toward the central singularity. In this inverted realm, moving forward in what was once space is as inevitable as moving forward in time is for us. Some theoretical models of the black hole interior propose that this role reversal could lead to a state of pure chronological chaos. Without time acting as the steady flow that orders cause and effect, events could occur in a jumbled, non-sequential mess. The past, present, and future might not just overlap, they could become completely indistinguishable, a tangled knot of reality with no beginning and no end. This is where the infamous information paradox becomes critical. According to quantum mechanics, information about an object, the specific arrangement of its particles, can never be truly destroyed. Yet, if an object falls into a black hole and is lost forever in the singularity, that information seems to vanish from our universe, violating a fundamental law. Physicists now believe the solution to this paradox might lie in a radical rethinking of time itself. Perhaps the information is not destroyed, but instead becomes scrambled and encoded onto the event horizon in a way that profoundly disrupts our linear timeline. The act of falling into a black hole might not be an end, but a transformation into a state where your history is rewritten and your future is entangled with your past. By studying these gravitational extremes, we are not just looking at distant curiosities. We are peering into a natural laboratory where the universe itself is running experiments on the limits of time, showing us how the very fabric of cause and effect can fray and finally collapse under the right conditions. The origin of our timeline, the Big Bang, presents the ultimate paradox of beginnings. This cosmic event marks the start of everything we know, the expansion of space and the forward march of time. Yet the most profound question remains: what came before? If the Big Bang was the true beginning, then the concept of before might be meaningless, a question without a framework to contain an answer. Some cosmologists propose that time itself did not always exist, that it emerged from a state of timelessness, a singularity where all known laws of physics break down. In that initial fireball, the conditions were so extreme that the very distinction between time and space could have been fluid. This opens a startling possibility that chronological inversion was not just possible in the early universe, but perhaps even inevitable. In the first fleeting moments after the bang, the fabric of reality might have flickered, with events occurring out of sequence before settling into the stable flow we experience today. Think of it like a pot of water coming to a boil. For a moment, bubbles form and pop in a chaotic, unpredictable dance before settling into a steady, rolling boil. The early universe might have been that chaotic dance, a period of temporal turbulence where cause and effect were not yet firmly established. This leads to even grander cosmological models, like the cyclic or bouncing universe theories. These ideas suggest that our Big Bang was not a unique beginning, but merely one phase in an endless cycle. In these models, the universe expands, eventually contracts under its own gravity in a big crunch, and then rebounds in a new Big Bang. During that contraction phase, as all matter and energy are pulled back together, the arrow of time dictated by entropy could theoretically reverse. The universe would rush backwards towards its origin, stars would unform, galaxies would reassemble into primordial gas, and the cosmos would effectively reset its own clock. This is chronological inversion on the grandest possible scale, a universal rewinding of the tape. Another fascinating concept from quantum cosmology is imaginary time. This is not time as we imagine it, but a mathematical tool where time is treated like a dimension of space. In this framework, the distinction between past and future blurs entirely. There is no beginning and no end, just a seamless four-dimensional surface without boundaries. It is like the surface of the Earth. You can travel around it forever without ever falling off an edge. In this view, the Big Bang is not a violent beginning, but merely a point on that surface, like the North Pole on a globe. This model elegantly removes the problem of a singular beginning, suggesting that what we perceive as the start of time is just a feature of our limited perspective. By exploring these origin stories, we begin to see that the structure of time might not be the fixed, rigid thing we assume it to be. Its flow and its arrow could be properties that emerged as the universe cooled and settled down. If that is true, then the potential for that structure to falter, to invert or collapse under the right conditions, is woven into the very fabric of our cosmic history. The birth of the cosmos might hold the key to understanding its most profound and terrifying possible death. Our own universe might be just one page in an infinite cosmic library. Multiverse theories take these mind-bending ideas of temporal instability and project them onto a canvas of unimaginable scale. In this grand view, our reality, with its specific laws of physics and its unwavering arrow of time, could be a single possibility among countless others. Some of these parallel universes might operate under completely different rules where the fundamental constants are rearranged. In such a place, the second law of thermodynamics might not apply at all, or it might work in reverse. Imagine a universe where entropy naturally decreases over time. There, time's arrow would point backwards from its very beginning. Smoke would always coalesce into unburnt logs, shattered glass would always reassemble on tables, and stars would form from scattered stardust, growing brighter and more ordered as the eons pass. For beings in that reality, their yesterday is our tomorrow, and their birth would feel to them like our death. This is not a temporary glitch, but the permanent, natural state of their entire cosmos. The many worlds interpretation of quantum mechanics offers another fascinating pathway. It suggests that every time a quantum event occurs with multiple possible outcomes, the universe does not choose one. Instead, it splits, spawning new branches of reality where each possibility is realized. In this endlessly branching tree of existence, there could be universes where, at the moment of their creation, the arrow of time was set pointing in a different direction. Some branches might even experience flickering timelines where the arrow of time is not fixed, but oscillates between forward and backward, creating periods of immense order and chaos in a bewildering cycle. This perspective completely reframes the concept of chronological inversion. In the context of a multiverse, a collapse of time is not a universe-ending catastrophe. It is simply a different mode of existence, a variation in the theme of reality that is playing out somewhere else in the metacosmic landscape. It transforms the idea from a terrifying anomaly into a natural, albeit bizarre, feature of a much larger and more complex existence. The instability we theorize about for our own cosmos could be a stable, everyday reality for another. This forces a profound shift in our thinking, moving the question from could time collapse to where and when does it already happen. These theoretical possibilities now have a physical form in cutting-edge laboratories. Scientists have created structures that defy our most basic expectations of time itself, known as time crystals. Unlike any other form of matter, a time crystal does not settle into a stable, motionless state. It exists in a perpetual cycle of oscillation, repeating its pattern over and over, but it does this without consuming any energy. It is a clock that winds itself forever. This bizarre behavior breaks what physicists call time translation symmetry, the expectation that the laws of physics will behave the same at every moment. For a time crystal, time is not a uniform flow, it has a built-in rhythm, a periodic structure where certain moments in its cycle are fundamentally different from others. To grasp this, imagine a gear that clicks into a new position every few seconds, not because it is being turned by a motor, but simply because that is its natural, preferred state of being. It is a form of matter that is permanently out of step with the steady tick of cosmic time. This is only possible because time crystals exist in a state of non-equilibrium. They are never still, never settled, forever dancing to their own internal rhythm. In these carefully controlled quantum systems, researchers are observing how the arrow of time can develop a wobble. Under specific conditions, the sequence of events within the crystal can appear to briefly invert or form a tiny, stable loop. It is a microscopic model of chronological disorder, a pocket of reality where cause and effect are not a straight line but a circle. While this is a far cry from stars burning backwards or people living their lives in reverse, the principles are profoundly connected. These experiments provide a tangible, observable window into how time can behave when the normal rules are suspended. They show us that temporal instability is not just a philosophical puzzle or a mathematical curiosity. It is a physical phenomenon that we can create, measure, and study. By probing these strange quantum systems, physicists are building a bridge from the most abstract theories about black holes and the multiverse down to the concrete world of laboratory science. They are beginning to understand the mechanisms that could allow time's arrow to bend and perhaps one day to break. If the timeline were to snap, the very idea of responsibility would vanish into chaos. An action you commit tomorrow could become the cause of an event that happened yesterday, unraveling any coherent notion of choice or consequence. Your free will would be an illusion, a phantom sensation in a universe where decisions are made after their outcomes have already been set in stone. Your identity, the story you tell yourself about your own life, would crumble. Memories would not be records of a fixed past, but fleeting, unreliable impressions that shift and change as the causal winds blow in reverse. You might suddenly recall a future event with perfect clarity, or completely forget a childhood that has not yet been unlived. Philosophers have wrestled with the nature of time for centuries. Immanuel Kant argued that time is not something we discover in the world, but a fundamental framework built into our own minds, a lens through which we necessarily perceive reality. If that lens were to shatter, would our consciousness simply break, or could it adapt to a world without sequence? Another thinker, John McTaggart, famously claimed that time is an illusion because events seem to have contradictory properties, being both past, present, and future. Chronological inversion would be the ultimate proof of his paradox, a state where every event is all three at once. This is not just a physics problem, it is a profound existential crisis. It forces us to ask what is more fundamental, the laws of physics or the logic of our own minds. Could reality operate with a completely different set of rules, where effect precedes cause without creating a paradox? Or would the universe simply refuse to compute, like a computer encountering a fatal error? The collapse of time would be more than a cosmic disaster. It would be the end of meaning itself, transforming human experience into a nonsensical dream where every moment is both a beginning and an end, and nothing is ever truly real. Our minds are already equipped with a strange and flexible sense of time. We perceive it as a steady, linear flow, but this is a carefully constructed illusion built by our brains. Under certain conditions, this internal clock can warp and stutter dramatically. In the intense focus of a life-threatening accident, seconds can feel like minutes. A boring lecture can make an hour drag on for what seems like an eternity, while a joyful afternoon with friends vanishes in a blink. Our dreams are a perfect example of this malleability, where narratives that feel like they last for hours unfold in mere minutes of rapid eye movement sleep. Psychologists have studied these distortions for decades, understanding that emotion, attention, and even neurological conditions can radically alter our personal experience of time's passage. Certain drugs or medical events like seizures can induce states where the sequence of events becomes jumbled, where a person might perceive the effect before they witness the cause. This reveals that our brain does not simply record time, it actively constructs it, stitching together sensory information into a coherent story of before and after. Now place this adaptable, fragile system into a universe where chronological inversion is real. if the external world truly began to unravel with causes and effects reversing, how would our internal perception cope? At first, it would be a nightmare of confusion. Your memories would clash violently with the reality unfolding before your eyes. You might have a vivid memory of eating breakfast, while simultaneously watching the cereal pieces leap from your stomach back into the bowl. The cognitive dissonance would be overwhelming, likely causing severe psychological distress, a complete breakdown in our understanding of the world and our place within it. But would we adapt, just as the brain can learn to interpret the distorted signals from a pair of inverted goggles, eventually making the world look right side up again? Could our consciousness learn to navigate a reversed timeline? Perhaps we would develop a new kind of perception, where anticipation feels like memory and recollection feels like prophecy. The very concepts of regret and intention would transform beyond recognition. This deep intersection of physics and psychology suggests that time is not just a feature of the universe out there, it is a fundamental part of the universe in here, within our own minds. A collapse of time would not just change the cosmos, it would rewrite human consciousness itself, merging the objective and the subjective into one bewildering, paradoxical experience. Science fiction has always been our first telescope into these impossible realms. Long before physicists wrote equations about closed time-like curves, authors like H.G. Wells were building machines to travel along them. His novel, The Time Machine, was not just an adventure story. It was a profound exploration of cause and effect, showing a future shaped by the social divisions of his own present. This tradition of using time as a narrative device has only grown richer. Films like Christopher Nolan's Tenet take the idea of inversion literally, presenting a world where entropy can be reversed for objects and people, creating breathtaking scenes of bullets flying back into guns and explosions unfolding in reverse. These stories do more than just entertain. They give us a visceral, emotional vocabulary for concepts that are otherwise trapped in abstract mathematics. We feel the disorientation of a protagonist meeting their future self. We grapple with the haunting paradox of a warning sent from tomorrow that creates the very catastrophe it hoped to prevent. Through these narratives, we explore the deepest human questions about fate and free will. If you could see your future, would you be bound to it? Does knowing an event will happen make you responsible for causing it? Science fiction allows us to live inside these questions, to test our moral and philosophical boundaries from the safety of a book or a cinema seat. It makes the terrifying idea of chronological collapse tangible, transforming it from a cold theory into a human story of memory, identity, and consequence. This creative groundwork is invaluable. It primes our imagination, fuels public fascination, and often inspires the next generation of scientists to ask, could we? The line between science fiction and science fact has always been porous, a frontier where today's wild speculation becomes tomorrow's laboratory hypothesis. By painting pictures of time's end, art gives science a destination to look for. The search for proof moves from blackboard equations to the controlled chaos of the laboratory. While no one has witnessed a star burning backwards, certain quantum experiments deliver results that defy a simple linear narrative. In these tests, particles seem to make decisions based on information from their future, a phenomenon known as retrocausality. It is as if a detective solves a crime before the murder weapon is even chosen, a tiny but profound hint that cause and effect might not be the rigid chain we believe them to be. These are not errors in measurement, they are repeatable outcomes that force physicists to consider that the arrow of time might have a tiny, inherent flicker at the smallest scales. Beyond the quantum realm, we have a fossil record of the cosmos itself. The cosmic microwave background radiation is the faint afterglow of the Big Bang, a snapshot of the infant universe. By meticulously mapping its subtle imperfections, cosmologists can trace the timeline of cosmic evolution backwards, almost to the very beginning. This data acts as a constraint, telling us what could and could not have happened in those first volatile moments, ruling out some wilder theories of temporal turbulence while leaving the door open for others. To push further, scientists use immense particle accelerators, recreating the extreme energies of the early universe to see if time itself behaves differently under such conditions. Supercomputers run complex simulations, modeling universes with different physical laws to see if a reversed or unstable arrow of time is even a possible outcome. The evidence is not yet conclusive, but the very act of looking changes the game. This empirical hunt transforms chronological inversion from a purely philosophical puzzle into a tangible scientific question. It encourages a cautious optimism that the deepest secrets of time may not remain secrets forever, but are waiting in the data, ready for the right experiment to reveal them. Mathematics translates these mind-bending ideas into a precise and testable language. The equations of differential geometry and topology provide the tools to map the warping of space-time, to describe how its fabric could twist into a knot or form a closed loop. These are not just abstract symbols, they are the blueprints for reality's most extreme architecture, allowing us to calculate what happens when gravity becomes so intense that it folds time back onto itself. A key technique used by theorists is called Wick rotation. This is a mathematical trick where you treat the dimension of time as if it were just another dimension of space. By making this substitution, physicists can solve incredibly complex equations that would otherwise be impossible to crack. It is like trying to understand a complex sculpture by studying its shadow from different angles. This method allows researchers to model scenarios where the distinction between past and future blurs into irrelevance, revealing pathways through the space-time continuum that defy our everyday logic. In advanced theories like string theory and loop quantum gravity, this mathematical approach suggests that time itself might not be a fundamental building block of the universe. Instead, it could be an emergent property, a collective rhythm that arises from the interactions of more basic elements, much like the temperature of a gas emerges from the chaotic motion of countless molecules. These frameworks provide equations that describe how time could potentially emerge, dissolve, or even invert under the right conditions. They offer a glimpse into a deeper layer of reality where our familiar sequence of cause and effect is just one possible configuration. This rigorous mathematical foundation is what turns wild speculation into a legitimate scientific pursuit. It transforms a terrifying philosophical question into a series of calculable problems, giving us the first real tools to ask not just if time can collapse, but how. Power to rewind time would carry a burden of responsibility unlike any other. If we could invert a sequence of events, even on a small scale, we would immediately face a profound moral dilemma. Would it be ethical to erase a mistake, even if that mistake led to a painful but necessary lesson? Could undoing a tragic accident inadvertently prevent the birth of a person who would later make a great contribution to the world? Every action, no matter how small, ripples through the timeline in ways we could never fully predict. The desire to prevent suffering is a powerful human impulse, but intervening in the causal chain could create unintended consequences far worse than the original event we sought to undo. This responsibility echoes debates we are already having about other powerful technologies, like artificial intelligence or genetic engineering. We wrestle with questions of whether we should do something just because we can. But with time manipulation, the stakes are not just global, they are cosmic. The ethics here would force us to define what we value most about existence itself. Is it the pursuit of a perfect, pain-free timeline, Or is it the messy, unpredictable, and authentic journey that shapes who we are? Philosophers argue that our moral compass is built upon a foundation of cause and effect, of actions and their consequences. If we sever that link, we risk unraveling the very concept of right and wrong. A scientist who gains the ability to manipulate time would hold a power that demands a new kind of wisdom, one that prioritizes the sanctity of the entire timeline over the desire to correct its flaws. This is not just a theoretical puzzle. It is a crucial reminder that the pursuit of knowledge must always be paired with a deep sense of ethical caution, ensuring that our curiosity does not outpace our compassion for the fragile tapestry of reality. This universal human obsession with time's nature is mirrored in the vast tapestry of cultural beliefs. Western thought often frames time as a linear arrow, a straight path from a singular past toward an open future, a narrative that aligns closely with our scientific understanding of entropy. But this is only one way to perceive the flow of existence. Many Eastern philosophies, like Hinduism and Buddhism, view time as a great wheel, an endless cycle of creation, preservation, and dissolution. In this cosmology, the universe itself breathes, expanding and contracting in vast epochs, and the end of one age is simply the beginning of the next. This cyclical model bears a striking resemblance to the bouncing universe theory in cosmology, where a big crunch leads to a new Big Bang. The concept of chronological inversion is not a terrifying anomaly here, but a natural, expected phase in the eternal rhythm of the cosmos. Indigenous traditions often offer a third perspective, where time is not linear or cyclical, but a deep, spiritual present. In these worldviews, the past is not a distant point on a line, but a living reality that can be accessed through ritual, story, and memory. The ancestors are not gone, they are a constant, guiding presence. This collapses the distance between then and now, creating a kind of eternal now where all moments coexist. The Australian Aboriginal concept of the dreamtime is a profound example, a sacred era of creation that is both the beginning of all things and a dimension that exists parallel to our daily lives. These diverse interpretations reveal that the scientific idea of time's collapse resonates with ancient human intuitions. The Maya predicted great cycles of world renewal. The Norse myth spoke of Ragnarok, an end that is also a rebirth. These are not just stories, they are frameworks for understanding the possibility of a universe that can reset, reverse, or transcend its own timeline. This cultural lens does not disprove the physics, but rather enriches it, showing that our struggle to comprehend time's fragility is a fundamental part of the human experience, a thread that connects the equations of Einstein to the visions of a shaman. Our perception of time is deeply woven into our identity, our rituals, and our very sense of meaning in the world. The equations hint at a future where time itself becomes a tool. Though these ideas exist only on paper today, the potential for technological application is a thrilling frontier. Imagine a quantum computer not merely using superposition, but actively harnessing microscopic temporal loops. These fleeting inversions could allow it to process information in a way that defies linear logic, solving problems in a single computational step that would take a conventional machine the lifetime of the universe to crack. We are not building these machines yet, but the theoretical groundwork is being laid, suggesting that the key to unimaginable processing power might lie in learning to manipulate the flow of cause and effect itself. Beyond computing, we can speculate about sensors designed to detect the faintest ripples in chronology. Just as seismographs warn us of earthquakes by sensing vibrations in the earth, a chronal sensor could one day alert us to anomalies in the fabric of time, perhaps near intense gravitational fields or in high-energy particle experiments. This would transform our observation of the universe from a passive act into an active listening, tuning our instruments to the very rhythm of space-time. On a more speculative level, if we could ever learn to control inversion, even in a limited way, it might open doors to revolutionary energy solutions. Could we tap into the energy differential between a forward-moving timeline and a reversed one? Or what about communication, not across distance, but across time itself, sending a message backward along a closed loop to be received in its own past? While this sounds like the wildest science fiction, history is filled with examples of today's impossibilities becoming tomorrow's innovations. The concept of the laser was once a mere theoretical curiosity in Einstein's papers. The idea of splitting the atom was a fantasy before it became a reality. Our understanding of time is still in its infancy, but by daring to dream about its collapse, we are not just engaging in fantasy. We are planting the seeds for a future revolution, one that could fundamentally alter our relationship with technology, energy, and reality itself. The evidence for time's collapse may forever lie just beyond our reach. To even begin testing these theories, we would need to recreate energies and gravitational fields that dwarf anything we can produce in our most powerful particle accelerators. The conditions inside a black hole or at the moment of the Big Bang are not simply extreme, they are practically unreproducible with our current technology. Our most advanced tools are like trying to hear a whisper from across an ocean, utterly insufficient for the task. Even if we could generate such a fleeting moment of inversion, we immediately face a deeper, more philosophical problem. How would we even know it happened? The very nature of a chronological glitch might make it completely undetectable from the inside. If cause and effect reverse, the event that triggers our measuring device could occur after the device has already registered the reading, creating a logical loop where the evidence erases its own cause. It would be a fire that casts no shadow, a sound that leaves no echo, a crime scene that cleans itself before the detective arrives. This forces scientists into a delicate dance, designing experiments that can test the boundaries of physics without completely violating the foundational logic that makes science possible. They search for subtle secondary effects, tiny anomalies in particle behavior or faint whispers in cosmological data that might hint at a deeper temporal instability. The quest is a testament to human curiosity, a drive to understand the universe even when it seems determined to hide its most profound secrets. It is a humbling reminder that some mysteries may remain unsolved, not for a lack of trying, but because the universe operates on a scale and under rules that we are only beginning to glimpse. The value is not just in the answer, but in the questions we are forced to ask along the way. Your morning coffee cools as you pour it, the steam retreating into the pot. You step out of bed already dressed, the day unraveling in reverse. In this world, a handshake is an ending, a goodbye is the first thing you say. Your most cherished memories would not be something you look back on with fondness, but an event you are moving inexorably toward, a future meeting you have not yet had. Your greatest achievements would dissolve before your eyes, a masterpiece painting slowly emptying itself of color until only a blank canvas remains. Even our deepest regrets would transform. That hurtful word you once spoke would not be a moment of shame from your past, but an encounter you are destined to have, a conversation you're walking backwards into, powerless to stop the unkindness from leaving your mouth and entering the ears of a friend. Relationships would become impossible puzzles. You would meet someone for the first time at your emotional divorce, your shared history with them a story you are both unknowingly erasing with every backwards glance. Love itself would be a strange and fleeting sensation, a feeling of intense familiarity that grows weaker with every interaction until it finally vanishes at the moment you first lock eyes. This thought experiment is more than a fantasy. It is a window into how fragile our identities truly are. We are the stories we tell ourselves, a narrative built on a foundation of cause and effect. If that sequence crumbles, the very essence of who we are unravels with it. Our lives are not just a collection of moments, but the specific, irreversible order in which they occur. To lose that order is to lose the meaning we derive from every experience, every connection, and every choice we have ever made. Carlo Rovelli, a theoretical physicist who has spent decades pondering the nature of time, offers a humbling perspective. He suggests that our common-sense understanding of time is likely wrong, a crude approximation of a far more complex reality. In his view, the flow of time might not be a fundamental feature of the universe, but rather an emergent property that arises from our own limited perspective and our interactions with the world. This idea directly challenges the very foundation of chronological inversion, not by dismissing it, but by reframing the entire question. If time is not a primary element, its collapse is not the breaking of a rule, but a shift to a different mode of existence, one where our notions of before and after simply no longer apply. Another leading voice, physicist Lisa Randall, explores these extremes through the lens of cosmology and extra dimensions. Her work often asks how the laws of physics behave in environments we cannot naturally access. When considering the possibility of temporal chaos, she might point to the necessity of a consistent physical framework. Even in a scenario where cause and effect are inverted, the universe must still obey its own internal logic, however strange that logic may appear to us. The mathematics must still work out, preventing true paradoxes from unraveling reality itself. This is not a dismissal of the idea, but a call for a deeper, more robust theory that can accommodate such bizarre possibilities without self-destructing. To bring in a philosophical angle, a thinker might argue that the concept of inversion is a logical impossibility. If an effect truly preceded its cause, how could the cause ever come to be? The very idea seems to create an unsolvable loop that reality would simply refuse to compute. Yet, a cosmologist could counter this by pointing to the quantum realm, where particles routinely exist in blurred states of possibility, and to the event horizons of black holes, where our standard logic famously breaks down. These expert views do not provide easy answers. Instead, they paint a picture of a vibrant, ongoing debate at the highest levels of science and philosophy. They show us that questioning the flow of time is not fringe speculation, but a central puzzle in our quest to understand the cosmos. By listening to these diverse voices, we gain a crucial insight that the greatest mysteries are not solved by choosing one idea, but by holding multiple, conflicting possibilities in mind until the evidence compels us to see the universe in a new way. The twin paradox is a classic demonstration of time's fluidity, where one sibling returns from a high-speed journey through space to find their twin has aged far more than they have. This is not a thought experiment, it is a confirmed prediction of relativity, a real-world example of how motion warps personal time. But let us push this idea to its absolute extreme. What if the conditions for time dilation were so severe that they did not just slow time, but shattered its linear progression entirely? Imagine one twin not just aging slower, but beginning to age backwards, their life unwinding in reverse while the other moves forward. They would not just be different ages, they would be living in opposite temporal directions. The reunion would be a moment of pure paradox, a collision of two irreconcilable timelines. This is the terrifying leap from dilation to full inversion, where the rules of cause and effect governing each twin's reality are no longer aligned. Their shared history would fracture, their memories of childhood together becoming impossible to reconcile as one remembers a past the other has not yet lived. This case study shows that the weirdness of relativity is not a distant curiosity. It is a hint that time's arrow is not an absolute law, but a condition that can be bent and potentially broken. We can speculate further on variations of this collapse. What if the inversion was not a single, clean reversal, but a series of flips where a person's timeline oscillates between moving forward and backward, creating a chaotic jumble of experiences? Or consider a scenario where the inversion is localized, creating bubbles of reversed time within our normal flow, where objects or even people might flicker in and out of existence as their causal chains tie themselves into knots. These are more than just wild speculations. They are logical extensions of the physics we already know to be true. The twin paradox grounds the unbelievable in a relatable human story, making the abstract threat of chronological collapse feel personal and immediate. It forces us to ask, if time can be stretched for one traveler, what would it take to snap it completely? The hunt for time's secrets is accelerating in laboratories around the world. Scientists are now designing ingenious experiments to probe the limits of causality, using tools far more precise than any thought experiment. In ultra-cold quantum gases, researchers can create conditions where atoms behave as a single collective entity, a Bose-Einstein condensate, allowing them to observe quantum effects on a visible scale. Within these strange states, they can test if information can be subtly influenced by future events, searching for the faintest whisper of retrocausality. Meanwhile, gravitational wave observatories like LIGO and Virgo are listening to the echoes of cosmic collisions, the ripples in space-time caused by black holes merging. Each detection is a new data point, helping us map how the fabric of reality behaves under the most extreme stress, potentially revealing anomalies that could hint at temporal instability. The Event Horizon Telescope, which gave us the first image of a black hole's shadow, continues to refine its view. By studying the plasma swirling at the very edge of these monsters, we might one day detect a signature of the role reversal that happens inside, where time and space swap their fundamental properties. This is not work for a single discipline. The puzzle of time demands a convergence of minds. Physicists provide the equations and the experimental frameworks. Mathematicians develop new tools in topology and geometry to describe how space-time can fold, and philosophers grapple with the profound implications, ensuring our questions remain sharp and our interpretations are sound. Even the push for more powerful quantum computers plays a role, as building them forces us to understand decoherence and quantum information in ever deeper ways, concepts that are intimately tied to the arrow of time. This collaborative, global effort transforms a terrifying cosmic question into a series of solvable, incremental puzzles. It means that the mystery of time's collapse is not a dead end, but an active frontier, with new discoveries waiting just over the horizon for those who dare to look. This is not a wizard spell or a plot device from a movie. Chronological inversion is a serious, though highly theoretical, scientific concept grounded in the complex mathematics of general relativity and quantum mechanics. It is crucial to distinguish this from the time travel we see in popular culture. You will not find a DeLorean or a police box here. Time travel stories typically involve a traveler moving along a pre-existing timeline, like a train on a track, potentially creating paradoxes like killing your own grandfather. Inversion is far more radical. It is not about a journey on the timeline. It is about the track itself twisting, breaking, and splintering into a chaotic mess. There is no traveler, no machine, and no clear destination. The paradoxes of inversion are not logical puzzles to be solved by a clever hero. They are fundamental breakdowns in the structure of reality itself, where the very concepts of problem and solution may cease to have any meaning. The media often sensationalizes these ideas, blending science with fantasy until the line between them blurs beyond recognition. This does a disservice to the profound and genuinely strange reality that physics suggests. The goal is not to dismiss creativity, but to build a foundation of critical thinking by separating the rigorous, if speculative, science from pure science fiction. We empower ourselves to engage with these incredible ideas without confusion. We can appreciate the storytelling while also understanding the real and far more terrifying possibilities that our universe might truly hold. Some interpretations of quantum mechanics place the observer at the very heart of reality. This participatory universe theory suggests that consciousness is not a passive witness to events, but an active force that helps to solidify them from a fog of probability into a definite timeline. Your own awareness, the simple act of noticing the world, might be a fundamental part of the cosmic clockwork. This idea forces a profound question. If the flow of time were to invert, would our consciousness be a rigid structure that shatters under the strain, or a flexible process that could learn to navigate the chaos? Neuroscience offers a clue. Our sense of a linear timeline is already a construction, a story our brain tells itself by stitching together sensory inputs, memories, and anticipations. This internal narrative creates the seamless illusion of a past, present, and future. What happens when the external world stops supplying data in the correct order? Imagine your eyes seeing a shattered vase reassemble on the floor, while your brain simultaneously holds the memory of it being whole on the table just a moment before. The cognitive dissonance would be overwhelming, likely causing a complete breakdown in our ability to function or even maintain a stable sense of self. Yet the brain possesses a remarkable capacity for adaptation. There is a haunting possibility that consciousness could, in theory, rewire itself. It might learn to interpret a backwards causal chain, where anticipation feels like memory and recollection feels like prophecy. Your deepest regret might transform into a future event you are moving toward, a destined mistake you have not yet made. This merges physics with the deepest philosophical puzzles about free will and identity. If you are living your life in reverse, are you truly making choices, or are you merely acting out a script that has already been written in what you would perceive as your future? The collapse of time would not just be a physical event, it would be a psychological and existential unraveling, forcing us to ask if the mind is a prisoner of time or its co-creator. This makes the mystery intensely personal, inviting you to ponder your own role in weaving the fabric of reality, moment by moment. The immense gravity of a neutron star is so powerful it warps the very vacuum of space around it. These cosmic remnants, packing more mass than our sun into a city-sized sphere, create gravitational tides that could theoretically stretch and compress the timeline itself. Near their surfaces, the fabric of spacetime is contorted to an extreme degree, potentially creating microscopic zones where the orderly progression of cause and effect falters under the strain. This is not a gentle bending, but a violent twisting that might briefly open a doorway to temporal chaos. We can observe the effects of this through pulsars, neutron stars that emit beams of radiation like cosmic lighthouses. The incredible precision of their pulses is a testament to stable physics, but it also makes them perfect natural laboratories. Should one of these pulses ever arrive out of sequence or exhibit a bizarre inverted pattern, it could be the first evidence of a localized time anomaly, a flicker of inversion in the deep void. Beyond these known objects, the universe holds even greater mysteries capable of triggering such an event. The vacuum of space is not truly empty, but seethes with quantum fluctuations, where particles and antiparticles spontaneously pop into and out of existence. Under certain conditions, perhaps within the concentrated dark matter halos of galaxies, or at the epicenter of a cataclysmic gamma-ray burst, these fluctuations could be amplified on a macroscopic scale. A gamma-ray burst, releasing more energy in a few seconds than our Sun will in its entire lifetime, might pour enough energy into a localized region of spacetime to briefly overwhelm its structural integrity. For a fleeting instant, the timeline in that region could stutter, invert, or tie itself into a knot before the energy dissipates and the normal flow of time reasserts itself. These events would be unimaginably violent and rare, but their possibility transforms the night sky. That faint, distant twinkle of a star might not just be a point of light, but the aftermath of a cosmic event where time itself momentarily broke its own rules, a silent testament to the fragile and dynamic nature of reality itself. The journey to understand time does not end here. If these ideas have sparked your curiosity, a wealth of resources is waiting to guide you further. For a deep and beautiful exploration of these concepts, the books of physicists like Brian Greene or Carlo Rovelli are a perfect starting point. Greene's The Fabric of the Cosmos elegantly unravels the nature of spacetime, while Rovelli's The Order of Time offers a poetic and profound meditation on time's illusion. To hear these discussions come alive, tune into podcasts like Neil deGrasse Tyson's Star Talk Radio, where experts break down complex topics with enthusiasm and clarity. For visual learners, documentaries from PBS Nova and the BBC Horizon series provide stunning visuals and accessible explanations that bring theoretical physics to life. Your exploration can continue online with YouTube channels like Veritasium and PBS Spacetime offering deep dives into specific questions about black holes, quantum mechanics, and the arrow of time. To follow the very latest research, you can visit the websites of institutions like the Perimeter Institute for Theoretical Physics or CERN, where groundbreaking discoveries are happening right now. These resources are your portals to a wider community of learners, a place where curiosity is the only prerequisite and the greatest mysteries of the universe are an open book, waiting for you to turn the page. How would you spend a single day if time suddenly began flowing backwards? Your morning would start with the sunset, your dinner would be the first meal you eat, and every conversation would begin with a farewell. Now take that thought one step further. What pivotal moment in history would you choose to invert if you could? Would you want to see a terrible war unravel itself, its final peace treaty signed before the first shot is ever fired? Or perhaps witness a great discovery in reverse, watching a brilliant theory dissolve back into the simple question that sparked it, just to feel the raw wonder of not knowing. These are not just fun puzzles, they are windows into how deeply our lives are structured by the arrow of time. Our entire existence, from our daily routines to our collective history, is built upon a foundation of cause and effect. By imagining that foundation crumbling, we are forced to confront what truly gives our experiences meaning. Share your own scenarios in the comments below. Tell me what event you would invert and why. Your ideas might reveal something profound about what we value most when the sequence of events is no longer a certainty. This conversation is not just a one-way street. Your perspectives help shape the exploration, turning a solitary thought experiment into a collective dialogue about the most fundamental structure of our reality. We have journeyed from the quantum haze to the crushing depths of black holes, all to explore the startling possibility that time itself might not be a fixed river but a fragile thread. The theory of chronological inversion, while unproven, emerges directly from the deepest puzzles in physics, a logical extension of the bizarre rules that govern our universe. It is a concept born from the relentless rise of entropy, the warping of spacetime by gravity, and the probabilistic chaos of the quantum realm. This is not mere fantasy, but a serious scientific frontier that forces us to question the very foundation of cause and effect. The implications ripple far beyond equations, touching philosophy, challenging our notions of free will and identity, and even inspiring new technological dreams in computing and energy. Culturally, this idea resonates with ancient cycles of rebirth and modern stories of time's end, showing that our fascination with time's fragility is a profoundly human experience. While we may never witness a star burn backwards, the true value lies in the questions themselves. This pursuit ignites our curiosity, drives scientific inquiry, and reminds us that the universe is far stranger and more wonderful than we ever imagined. It leaves us with a renewed sense of wonder, not just about the cosmos, but about our own place within its fleeting, beautiful, and possibly unstable timeline. Our journey through the nature of time reveals a cosmos far stranger than we ever dreamed. The universe is not a static stage with a single, unwavering clock, but a dynamic and potentially unstable fabric where the past, present, and future might not be as separate as they feel. This exploration of chronological inversion, from the quantum foam to the singularities of black holes, is more than just theoretical physics. It is a fundamental re-examination of reality itself. These ideas challenge our deepest assumptions about cause and effect, memory, and identity, inviting us to see the cosmos not as a finished product, but as a continuous and perhaps fragile process. Every mystery we have touched upon is an open door, an invitation to look deeper and question further. Your curiosity is the most powerful tool in this endeavor, the spark that ignites discovery. Thank you for venturing into these depths. If this journey sparked your wonder, please like this video and subscribe for more deep dives into the universe's greatest secrets. Let me know in the comments what aspect of time's potential collapse intrigues or terrifies you the most. Until our next exploration, keep looking up and never stop questioning the incredible cosmos we call home.